So now I will be showing you how to analyze the results from your FEA analysis. So basically what we have done, we have completed the pre-processing phase, and now we are going on to the analysis phase, and then we will go on to the post-processing phase. There are certain outputs which SolidWorks already selects for you by default for a particular type of analysis. Depending on the type of analysis, you can see here a long or small list, but for a static analysis, the only output will be stresses and strains, and that's basically already included by default. So you don't really have to change these settings, and you can just accept the default settings. Now, to actually calculate the results, you will need to run this study. Okay, so you'll need to use the command on the top which says run this study, and when as soon as I click it, within less than a second the software will be able to evaluate the stresses and strains at all of those how many nodes we said, 1606 nodes, and for 6444 elements. So this is what the software is doing. As soon as I click, you can see in less than a second the software was able to not only calculate the results but also write it down to our computer. Now, if you look at this stress results right now, the quantity it is showing you is called as von Mises stress. But in the lectures, we have not yet covered the von Mises stress. Okay, I will be covering that in a few weeks later. So I don't want you to be confused by this, and I want you to edit this plot and change it to quantity which you have already know from your lecture sessions. So to do that, right click on this and you go to edit definition. So when you go on to the edit definition, it shows you the different quantities that it can output for you. So in the display, you select the which component, by the way, you think it will be out in this list. Anyone? In the class, what did we calculate? Was it a normal stress or a shear stress for this problem? Right? It was a normal stress, right? And it was along the length of the member, right? So that was a x direction normal stress that we were. So that's why the first option in the list, which is SX normal stress, is the one which is of most interest to us. Later on, I can show you the other components of the stress as well, but they will be of less interest. Okay. Now, the software also gives you some other options. I'm not going to change any of these other options for now, and I'll stick with the default output on the nodes. Okay. So that gives you a more refined set of results. If you output the values on the elements, then those will be the averaged value for each of those elements. Selecting the output on node will give you a more refined view. Okay. Now you have got two options here. One is to have a deformation scale based on an automatic scale factor, and then there is a true scale option. I will first select the automatic scale factor option just to show you what it shows, and then I will change it. So before I move on, I also want to change the units to megapascals because that's easy for me to read. And in terms of the chart options, I will go here and I will select the units as floating so that it just shows you as a standard number. And basically, I will also reduce the number of decimals to 2, and what I will be doing is I will be basically also asking the software to show the maximum and minimum, but I can do that later in a second. Okay, so I'll just say go back to definition, make sure everything is okay, and I then select OK. Now you can see here the software is plotting the X stresses, which is 108.51 as the maximum stress you can see from this legend over here. But right now you don't really know the exact location. You can basically manually check the results by, for example, clicking on the probe tool, or you can actually go back and you can click on the chart options again, and in this time I will say show max and show minimum. So it all automatically shows me where the maximum and the minimum is. One thing that you will notice here is that my force vector seems to be hidden behind the actual deformed shape. This is now a consequence of the fact that we used a very high scale factor. Okay? If you had not paid attention, you will think that this is a true feature. So let us now look into what this scale factor is. You can see on the box on the top, and it actually tells you that the scale factor is 347 times, meaning that if the deformation was only 1 millimeter, it will show it to you as 347 millimeters. We don't like that normally, but sometimes we need that information to just get a a visual comparison for some purpose. So I will actually go back and I will edit the definition, in the chart options. And in the chart options, I will have to go into the definition and I will actually click on the true scale instead of automatic, which means that a 1 millimeter deflection will only be shown as 1 millimeter on the screen. So with that, I'll just go back and now you can see the arrows are shown where they were, and now the deformation is not looking extraordinary. Now you can view this model and you can actually see the software is showing the highest stresses on these edges, but interestingly, it's also showing you the low stresses on the edges around here, which I already explained in the cause in the class is the cause consequences of the Poisson effect. So what you can also note down is by going into the probe tool, you can actually view and read the stress values at any of these locations. So for example, if I click at this location, it will show me a value of around 55.03 megapascals. Okay. Let's now try to compare these numbers with the hand calculated values that we had. So I go back to my Excel sheet where I have already recorded the number of elements and nodes in the previous step with you guys. Then I have here different other options that I can compare. In terms of my X stresses, which is this column, okay, the software is saying my maximum gross stress. So what was the gross stress? Gross stress was away from the notch. So it was in this area and it is around 55.03 megapascals. So I write this number down, 55.03 megapascals. The maximum stress from my finite element model in this case is going to be basically here. So it is 108.51. Okay. So 108.51. Okay. The minimum stress from the FEA model is 13.98. So I'll write it down, 13.98. Okay. Now you can immediately see I have written down the numbers that I calculated in the class with you. For our gross stress, the value was around 55.1. So you can see that this number is very close to the number that we calculated using hand calculations, and this number is pretty much accurate because there is no stress concentration there and the stress field was very uniform. So our assumption of uniform stresses to calculate these values through hand calculation was good over here. But in this region, what we see is that none of the values is actually is close, because our gross stress, our net stress value in this section is around 82.6, and the highest stress value was around 169.3 based on the stress concentration factor. So this was the value, the number that I calculated later on using our approach of stress concentration factors. This is coming from this slide that I solved for you in the class. So based on this number, we can see that we actually have a significant error of around 56% between our highest calculated value of the X stress and the value calculated using stress concentration factor approach. If you want to compare it with the net stress, then what you need to do is you need to actually go in the software and read the value which will be in that region. So around here maybe, okay, because we don't have a uniform, a singular value in case of our FEA. So this is around 64. So you can see that this is also away from the net stress estimate that we calculated in this region, which was around 82.6. Okay. So that means that there is a difference, big difference between the values from our software and the values that we hand calculated as far as the notched region is concerned. Then we have also we can compare the displacement along the x-axis. So to get some idea about our whether this error is because of incorrectly setting up the model, or this error is because of a genuine effect that we cannot account for in our calculations, we can go back and check our displacements. So displacement wise, you should see less error, because the displacement, as I indicated to you, is cumulative. So to see the displacement, right now this is plotting a equivalent displacement plot, okay, which is varying from 0 over here to a maximum value. But I don't want to compare the equivalent displacement, rather resultant displacement, rather I want to just compare the displacement along the x-axis. So I will again go to the defined displacement plot option, and on the defined displacement plot, I will click here and choose x displacement as my displacement option. I'll keep the units in millimeters, and I will again select true scale, okay, and I will in the chart options, again I will just use a floating point representation with 2 places of decimals, or 3 places of decimals is also okay, and I'll just select okay. And now you can see here that my displacement is coming out to be around 0.048 millimeters. So because this is a small number, I may want to increase the accuracy in terms of the precision. So I will actually go back to my chart options, and in this case I'll just select the scientific representation with 3 places of decimals. So now this is giving me my results. To get the maximum and minimum, I can again use the same feature in the chart options, which allow me to plot the maximum and the minimum. And as expected, the maximum displacement is at the end where the load is being applied, and the 0 displacement is basically at the end where it was fully constrained. Now this displacement is how much? 4.753 into 10 to power minus 2. So I can record that in my Excel sheet. So this is 4.75 into 10 to power, 4.753 I think it was, into 10 to power minus 2. Okay. So you can see here, in terms of the displacement, the error is actually quite small. It is only around 0.6%. Okay. So I've calculated the error by simply subtracting the FEA results from the hand calculated results, and then using FEA results as the basis for calculation of the percentage error. So I have done that, and you can see here, looking at this number will give me confidence that okay, there is no major problem in the model setup. If this number is also wrong, then you should reconsider, okay, because the displacement results are cumulative and they are not highly dependent on accurate calculation of stress concentration. Because if you remember in the class, we use this assumption over here, and then we calculated the total displacement, which I am comparing against. Okay, right. So since this number is okay, I can say that means basically the problem is I'm not really capturing the highest stresses in the most stress concentrated zone. So that is what I will be doing, and I will rerun now this analysis using different other mesh options, which will allow me to see the effect of the choice of mesh parameters on our results in finite element analysis, and I will then discuss these with you. For completeness sake, let me also plot 2 other plots, one for stresses along y-axis and one for stresses along z-axis. So I'll plot both of them as well. I'll keep the same chart options, keep it floating, and 2 places of decimals, the results being in megapascals, and showing the minimum and the maximum. So that's my plot for the y-axis. I can quickly copy this to avoid me from stop. Okay, so let me again define stress plot. Actually, I can just paste this again just to change this, edit definition, and I will actually select a new one. So that's the z-axis, and I can always then say okay. I need to rename this because this is no longer a copy. This is actually stress 2. Okay. Right. So this is stress 3 now. Okay. Now you can see here, interestingly, that your y and z-axis stresses from your hand calculations, you have no idea of what the y and z-axis will be, right? But from the computer generated values, because we have used a full 3D analysis, you can also see that what will be the values along the y and z-axis because of the Poisson effect. Actually, if you want to validate these numbers, you will need to go back and use the constitutive equations that I showed you in 2D and 3D. Remember, I think that was done in week 3. So I'm not doing that in the class, but if somebody wants, he can actually confirm some of those numbers by using those constitutive equations for the maximum stresses. So the maximum stresses along the y-axis is 21.97, which is because of the Poisson effect, and then the minimum is around minus 4.67. I'm not going to record this in my Excel sheet for now, just to save time. Now, once I'm happy with this, I can actually save this so that I can easily review these results later on. So I just click on save. Now, to run the analysis again, I will need to copy this analysis again, but I'll do that in the next video. So I'll just stop the video recording for now and do this again.